Hello students, welcome once again to Dr. Soros's classes. We are back again with some more fantastic videos on group theory. Okay, and we are doing the theory part. You know that in the previous video, if I go back to the previous slide, what we were doing is this, and we were more or less we have learned, we had gone through all this. And the important part that I had marked over here about the Clen4 group, okay, which is given by EABC. What is EABC is very simple to understand. E is the identity and ABC can be any element. So if it's multiplication, the identity is 1. Okay, the Clen4 group is abelian but not cyclic. Now a very simple logic how it is abelian but not cyclic is just a simple thing to understand. Okay, so let me just show you that how the K4 group, the K4 group is very important. That's why I'm emphasizing on the K4 group. Okay, the K4, the Clen4 group, say with elements 1 comma A comma B comma C. Okay, let us understand how this group is abelian. There is no need to understand that. Let's understand how this group is not a cyclic group. You see, as far as you should know is that to check that if it is a cyclic, to check, let's write that, to check if K4 is cyclic, all you need to do is simple. Take the numbers, take these numbers and see which generates the whole class. Let's find subgroups. So 1, of course the subgroup of 1 will be 1 only. Now the next one is A. So what can be generated? 1 comma A. Next one is B. So what can be generated? 1 comma B. Next is C. What can be generated? 1 comma C. Can you see anywhere any generator, any generator that is giving you like this? You see, any generator, say G, is giving you all the elements. Can you see? 1 comma A comma B comma C. Does it give you a subgroup of all the elements? Is it possible? No, it's not possible. You are not getting. Hence, the K4 is abelian but not cyclic. Okay, concentrate on this group. Very, very important. Okay, now moving on to our next parts. Okay, in the previous one we had done till only part 5. Now moving on to our next part. What does the next part say, students? It says that the next part says an infinite cyclic group is isomorphic to the additive group of integers. What is isomorphic? Let's not get into that topic now, because isomorphic is later on in this chapter. Isomorphic, automorphic, endomorphic, there are many more. Okay, homomorphism, there are many things that we need to understand. Okay, so let's not get on to this word in detail now. Just you must know that an infinite cyclic group is isomorphic to the additive group of integers. Okay, isomorphic, what it is, we will talk about it in the next videos later on, not now. You're going to get absolutely confused. Okay, any finite cyclic group of order n is isomorphic to Z. Okay, any finite cyclic group of order n is isomorphic. Okay, students. Okay, so what does it say? Any finite cyclic group of order n is isomorphic on Zn. What is just let me tell you what is isomorphic. It's just 1 to 1 and onto. When a function is 1 to 1, okay, just a vague definition. When a function is 1 to 1 and onto, okay, then that type of a function is called isomorphic. Alright, Alright students, so isomorphic is 1 to 1 and on to only, that much only you must remember. Let's move on to the next one. Any two finite cyclic groups of same order are isomorphic. Any two finite cyclic groups of the same order. So the order of the groups are same. They are two finite cyclic groups and the order is same. Okay, then they are isomorphic. Okay, moving on to the ninth topic. Ninth topic is very important. For some integer n, let's rub out everything over here. I may need to do some mathematical part on this also. Okay, let's say it's given. What does it say? It says, let's mark this as important. It says for some integer n greater than 1, okay, let G, the group G, be generated by the element A. The element A now be a cyclic group. G is also cyclic because it is generated by A. We are getting a generator. Okay, it's a cyclic group of the order n. Okay, since the identity, since E is equals to a to the power 0, a to the power 1, okay, a square, comma, dot 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 dot, right until a n minus 1, okay, are all distinct, all different, and for positive integer m less than n, so these elements are all different. Now if we can find a positive integer which is less than n, then what can we say? We can say that a to the power m is the generator, is the GEN of the group G. Alright, if m comma n is equal to 1, we get the number of generators of G, which is phi of n. Again we are going back to the UDAS function, right? Phi of n, you will find the number of generators that way, but provided if and only if m comma n is equal to 1. Alright, so what does it say? It says that for some integer n, we are already taking an integer n greater than 1, let the group be generated by some generator A. So it is a cyclic group of order n, then E will be equal to a to the power 0, comma, a to the power 1, comma, a to the power 2, right on till a to the power n minus 1. They are all distinct values, all different values. And for positive, any positive integer n, if I take any positive integer m with the condition that m is less than n, then I can write a to the power m to be a generator of group G, to be a generator of group G. Alright students, did you understand what's going on here? Isn't it? So if then you can get a generator, okay, when you get the generator, that will happen only if you need to check the condition that m comma n is equal to 1. Okay, then we get the number of generators of G is phi of n. You can also find the number of generators by using this phi of n rule. Okay, phi of n. So when you use this phi of n, this function, you will be able to find the number of generators. Moving on to our 10th part. Okay, subgroup of a cyclic group is cyclic, but the converse is not true. Very, very important. Very, very, very important. What does it say? It says that subgroup, so let's rub this off. Subgroup of a cyclic group is cyclic. Subgroup of a cyclic group is cyclic, but the converse is not true. That means if you have a cyclic subgroup, not necessary the group is also cyclic. It is not necessary, but the subgroup of a cyclic group will be cyclic. If the group is cyclic, then its subgroup is cyclic. But if the subgroup is cyclic, not necessary that the group will be cyclic. Okay. So students, in this part we learned some more important results on cyclic group, and we will be continuing this. There are little bit more examples, okay, some more properties or results on the cyclic group, and we will be continuing with this group theory videos. I will be giving you mathematical examples, as I keep telling you in each and every video. Mathematical examples are the main thing of this group. Eventually it will all come up to mathematics. You will have to answer difficult questions. So we will train ourselves, we will get ourselves prepared to answer difficult questions. So you keep taking as much help as possible from Dr. Soros's classes, because all the help that you'll be needing will be provided here at Soros's classes always. Thank you for watching, students. We shall continue this in the next video. Bye bye.